Bismillah ar-Rahman ar-Rahim. Today we'll discuss flow. The most important question which you may face during the oral examination is give a hint about the laminar flow and the clinical application of it. Now we can see from the figure the Hagen-Boisier equation, which equals pi time pressure difference and the diameter to the power of 4 over 128 eta and the length. These are the units of the denominator. Of course, you will be asked also what is the aim of it. You ought to tell them that I can use this equation when a patient is shocked, or if I want to increase the ventilation of the patient by increasing the diameter of the tube, as you can see in the figure. In shock patient, always we use white cannula, beginning infusion of the patient. Of course, there are other points, but the most important thing is to use a white cannula. Of course, you can increase the pressure of the fluids by elevating the infusion unit or decreasing its viscosity. All these are items. Now we come to what we call the turbulent flow. I will show you on the figures the difference between both of them. Now we come to the turbulent flow where we find that it is directly proportional to the pressure, inversely proportional to the length, and inversely proportional to rho. Rho is the figure of density. What are the critical aspects and the difference between both? Of course, whenever we know what we call the Reynolds number, which equals the linear velocity times pressure and the diameter over rho, over eta. All these are figures where we can estimate whether the flow will be laminar or turbulent. Of course, if this figure exceeds 2000, that means that the flow is turbulent. Of course, the most important thing is to try to minimize the velocity, and velocity is correlated to flow and on the type of the gas and the diameter. Of course, all these are figures you ought to minimize to reach to a laminar flow. Of course, there are many things that increase the laminar flow, as coughing, the peak in inspiratory flow, which is around 50 liters per minute, coughing, speaking. All this induces a turbulent flow. Also in the narrow airways, though they are narrow, but they have a laminar flow because the flow is slow. Now we will come to the analysis of the diagram we will be showing later, representing the difference between the flow of nitric oxide in 60% in oxygen or air at 20 degrees Celsius, or whenever I use expired air with CO2, the flow of such circumstances are differently. Of course, humidity decrease the density. This is very important, of course, to increase the critical velocity. In other words, whenever I say increase the critical velocity, means that there is a much more flow to increase the velocity. So it is more safe to say to increase the critical velocity or the flow. I will show you later on the paragraph. I'm sorry. Of course, helium decreases the density of the gas and it improves the ventilation. The second point, as regarding the graph I will show you later, the diameter of the tube. Whenever the diameter of the tube is corresponding to the flow, suppose we have an endotracheal tube 9 millimeter, the flow of 9 millimeter is convenient for the flow to be laminar and so forth. If I use the 22 millimeter of the tubing anesthetic circuits or the 30 millimeter of the scavenging system, all this are correlated to the flow. So whenever I want to have a laminar flow, this flow ought to be correlated to the size of the tube. What's the meaning of tension and surface tension? As we said before, surface tension is the forces on the surface of a liquid where it creates tension all over the surface. You see, the lining of the alveoli and the small air ways also induces surface tension. Whenever I mention tension, I mean that it is or correlation between pressure. Of course, pressure of most important to memorize pressure across the wall of the tube means the tension over the radius. Whereas if it is a sphere, we double the tension. So we say two time tension over radius because there are two planes of curvature regarding the sphere. The clinical application of it, of course, what we call the instability. You know, whenever we have a tube, of course, you ought to tell me. I don't have to explain to you, but when there is a correlation of the surface tension of the lining of the blood vessels and the pressure created by the radius. So whenever I decrease the radius, I ought to also decrease the surface tension to maintain the pressure. But it will come a time where the relationship between both of them will be lost, and at that time we say we have a critical closing pressure. This is also correlated also to the spheres. Suppose we have two alveoli. One of the alveoli is 200 micrometer and the other one is 100 micrometer. If we apply Laplace law on each of them, definitely the larger one will become more distended than the small one. So the bigger one will collapse the small one. This is not the case because we have what we call the surfactant. This surfactant controls the surface tension. It increases or decreases the concentration of it so that it can cope, so that the surface tension will be correlated to the radius, keeping the pressure so that there will no be instability or closing the alveoli. Viscosity is the resistance to flow. And we have, of course, whenever the hemoglobin or fibrinogen, as you said, I will ask you, what makes it increase? Of course, you will tell me, as you can see, the age and smoking and low temperature. And how can we decrease? Of course, we can decrease by low molecular weight dextran. And then after that, we'll come to the flow of Venturi. I will show it better on the figures where you can face a figure by the examiner to explain on the figure what are the important items of it. Of course, I will tell you what are the principle of it and who is Bernoulli who said that at a constriction the pressure is decreased because the velocity increased. So the decrease in the pressure is referred to Bernoulli. Of course, I will show you also later on what are the clinical application of the Venturi. We use an injector or a nebulizer or Venturi mask. All these are figures to be utilized by the Venturi system. Of course, you will be asked, of course, what's the entrainment ratio. The Quanda effect, I will show you later better on the diagram. This is the difference between the laminar and the turbulent flow. You can see that the laminar flow, the lines are straight. There is no turbulence, no eddies. But regarding the turbulent flow, as you can see, there is turbulence, there is eddies and swells. Of course, the flow is maximum as regarding laminar flow in the middle and becomes less whenever you reach to the surface. So smooth tubes at low rates of flow can initiate laminar flow. This is the ratio between the flow and the pressure. You see, they are linear, and the relation between both of them. Of course, we put a dot on the Q to denote the flow, not the quantity. The relation between both of them is the resistance. So whenever I increase the pressure, the flow is increased in a linear manner. This is how we estimate the resistance in a tube. Of course, we have a constriction, we have two pressures, and this is the flow. So the drop of pressure denotes the resistance. Of course, to perform an equation is difficult because the the turbulent flow is highly complex. This is the relation between the flow and the pressure. Of course, it's non-linear. The relation between both of them is different than that of the laminar. So you ought to increase much of the pressure to gain a flow. This is the most important diagram to show what the relation between the critical flow or the critical velocity. As we said before, the velocity is correlated to the flow. So this diagram shows the relation between the side, the diameter, and the critical flow. So when I compare air regarding nitrous oxide, 60% and 40% oxygen, what is the difference between both of them regarding the flow? Of course, as you can see from the diagram, if I extend the line downwards from the air to the nitric oxide, we will find that you can increase the flow of air at the same diameter without turbulence. On the other hand, the combination of both of them, nitrous oxide, oxygen, if you extend downward, you will find that you ought to have less than 30 to assure a turbulent flow in a 30 millimeter diameter. This is the explanation of the figure of the both of them. Of course, whenever I use carbon dioxide and humidity in expired air, this also decreases the density and increases the critical velocity. In other words, the velocity to be critical, you must have more flow. So this is difference. So air is much better than nitrous and oxygen regarding the flow at 30. You see, this is the explanation of both of them. Of course, these are the figures of the diameter of the endotracheal tubes and anesthetic circuits and the scavenging system. Whenever the endotracheal tube 9, suppose it corresponds to the 9 of the flow, the flow will be laminar. If we exceed the flow, the tube will be, the flow will be turbulence. This is the correlation between the pressure equals in a tube, tension over the radius. So whenever the tension is decreased, the radius ought to be decreased also to preserve the pressure. But if the radius is much decreased than the tension, the closing pressure will occur and will collapse the blood vessel. This is also correlated to the sphere. So the blood vessels and the bronchi are not rigid; they are malleable. They can increase and decrease accordingly. This is the figure to show Laplace law regarding the sphere, where if suppose there is no surfactant, this 200 or 200 micrometer diameter alveoli will extend much more than required, collapsing that of the small one. And this does not occur because the surfactant has the capability to manipulate the surface tension by increasing or decreasing its concentration, so that will keep the alveoli distended to extend to a spatial extent and not to collapse much. And this, of course, is important whenever we have we face a patient with problems regarding the neonates as regard the surfactant. This is the measurement of the viscosity. Viscometer, we have a cone where the liquid to be analyzed is administered through it, and then we have a torque or a torsion wire, and the movements of this torque regarding the resistance of the type of the fluid will get me a light over a mirror and reflected on a grade, so that we can know the viscosity of the liquid. Of course, we can denote that by the descent of the liquid in a tube. This meniscus, this meniscus has been also demonstrated by a light to denote its descent. This is the venturi, as we now know. This is the laminar flow, and then we come to having a constriction. Then we begin to raise the diameter of the tube to have the same diameter. At this point, the velocity is decreased, and the velocity is increased, and the pressure is decreased. You can see between we now this is the pressure. We are regaining the pressure at this part, but this pressure is being decreased according to Bernoulli's theory. Of course, there are two types of energy, the potential energy P correlated to the pressure and the kinetic correlated to the velocity. So you ought to know the two types whenever you are asked during the examination. And this is a clinical application. This is the injector. This injector, there is the flow here, and then there is an entrainment here because the pressure here is much decreased. So we'll suck. So I used to work in the past with in a theater, and they used to have a suction by applying this suction. They used to flow water from this side, and then this was attached to a suction tube where I can suck the patient because there is an entrainment here because the velocity is decreased and increased and the pressure is decreased. This is the nebulizer. Of course, this is a constriction, and we have fluids. This fluids is being entrained, and then it hits an anvil to make small droplets. And this is the venturi mask. Also, this tubing has a narrowing at the end. This narrowing will increase the velocity, decrease the pressure. So this decrease the pressure can make 1 liter of oxygen suck 9 liters of air. This is an important point of venturi mask. Meanwhile, the friction of the oxygen molecules with air also increases the entrainment. So whenever you ask what's the entrainment ratio, you're going to divide 1 oxygen over 9 liters of air. What is the back? Of course, whenever you have back pressure on any mask, of course, this will affect the function of the venturi. And this is what we call the Coanda effect, where we have a constriction after a laminar flow. But this constriction is being regained by 2 branches, you see. So you ought to say, okay, the flow will go to both branches equal. That's not the case. And this what happens in the blood vessels and small airways. And you can be asked why there is a part, this part does not undergo infarction, but this part goes in function because the flow has been shifted to one and leaving the other one. Now, can you use this Coanda effect by what we call the fluid logic, where we can make a flow going through this part. This can guide the flow from one side to other side, making a valve mechanism. You see, so we can utilize it in ventilators and save valves. This is a hint about the question you may be faced during the examination regarding flow. I hope that I succeeded. Wassalamu alaikum wa rahmatullahi wa barakatuh.